Algorithmic optimization is the process of finding the most efficient path to a specified goal among countless possibilities. Consider an everyday optimization problem. An ATM needs to dispense exactly 280 rupees, using the fewest number of bills possible. A greedy strategy makes the best possible choice available currently. It identifies the 200 rupee note as the largest immediate step. For the remaining 80 rupees, it selects the 50. Repeating this for the 20 and 10, it reaches the target perfectly. This logic operates under a specific constraint. It only considers the immediate present. It lacks the capacity to look ahead and see how current choices might impact the options available in later steps. Furthermore, the decision is irreversible. Once the algorithm selects a note, it commits to that path without any mechanism for backtracking or revision. This forward-only logic is a standard component in software, used for everything from mobile battery-saving protocols to delivery systems that prioritize the nearest drop-off point. Because it only calculates the next immediate step, the algorithm is highly efficient. However, this localized focus assumes that the best local choice will always align with the best global outcome, a premise that is not true for all datasets. While a greedy strategy successfully resolves the ATM example, its reliability depends on the mathematical structure of the problem. Without verifying that structure, the algorithm may fail to find the actual optimum. We can see where this heuristic breaks down by slightly changing the available data points. In this scenario, the target is 6, and our coin denominations are 4, 3, and 1. The greedy path selects the 4, leaving a target of 2. To reach it, the system uses 2 single-unit coins, totaling 3 coins. However, the true mathematical optimum bypasses the 4 and selects 2 3-unit coins, achieving the target with 2 coins. Because the local choice didn't lead to the best global result, the greedy approach failed. The mechanic of the failure is a direct result of the greedy rule. By selecting the largest immediate gain, the system was locked out of the more efficient combination of smaller values. Since the algorithm cannot backtrack, it is unable to correct the mistake once the first coin is selected. This demonstrates that a greedy strategy requires a formal architectural framework to ensure it is only applied to problems where localized choices are guaranteed to be correct. Engineering a stable greedy algorithm involves a standardized 6-step process. The process begins by defining the objective, whether to maximize or minimize a value, and then identifying every possible choice. This leads to step 3, defining the greedy criterion. This criterion is the mathematical rule that dictates every local decision the algorithm makes. This rule varies by problem. It might be the highest profit-to-weight ratio in a knapsack problem, or the shortest edge in a network graph. Once a choice is made, step 4 adds it to the solution, and step 5 removes any remaining options that are no longer valid. Finally, step 6 commands the system to repeat this loop until no valid choices remain. It is important to note the absence of any undo or retry logic in this architecture. While this loop handles the execution, it does not guarantee correctness. For that, we must look at the mathematical properties of the problem itself. To ensure the algorithm produces an optimal result, the problem must satisfy 2 specific mathematical constraints. The first is the greedy choice property. This property means that a locally optimal choice, the best decision right now, leads directly toward a globally optimal solution. This constraint focuses solely on the validity of the current immediate choice. If this property holds, taking the immediate best option will never prevent the algorithm from reaching the best possible final outcome. The second constraint is optimal substructure. Optimal substructure exists when the optimal solution to a large problem can be built by combining the optimal solutions of its smaller subproblems. For example, if the shortest path from A to D passes through B and C, the segments between those points must also be the shortest possible paths. While the greedy choice property validates the current step, optimal substructure validates the structure of the remaining decisions. The distinction is key. One ensures the first step is correct, while the other ensures the rest of the problem can be solved by repeating that same logic. A greedy algorithm can only be reliably deployed when a problem mathematically possesses both of these properties. By combining these mechanics and mathematical proofs, we arrive at a formal 7-step design protocol. The first half involves defining the objective, identifying the choices, and establishing the greedy criterion. The next phase requires proving that the greedy choice property and optimal substructure are both present in the problem. Only after these proofs are established do we write the code and analyze the final time and space complexity. This protocol highlights the architecture's trade-offs. When supported, greedy algorithms minimize execution time and memory, offering an efficient solution. However, these efficiencies lack safety nets. They require rigorous proof because they cannot recover from incorrect initial choices. Not every optimization problem can be resolved using this logic, which places a clear limit on the greedy paradigm. Ultimately, the greedy strategy represents a trade-off between simplicity and certainty. When the required mathematical properties are present, it is highly effective. When they are absent, it fails to find the optimum. In the next module, we will apply this 7-step theoretical framework to the fractional knapsack problem to calculate its precise time and space complexity.